We're looking on page 8 of your unit handout. This is the second lesson. This is called the remainder theorem. And between today's lesson and the lesson that we're going to get going with on Monday, these two lessons together are very important in terms of the algebra used to analyze polynomial functions. Today we're going to be looking at the remainder theorem. What we're looking at on Monday and also Tuesday is called the factor theorem. So what we're going to be looking at today is dividing algebraic expressions. And we're going to start off by reviewing how you divide numbers and the relationship between all the players in division. But we're going to be dividing polynomials. All of these things we looked at yesterday, all of these things we've identified as polynomial functions, we are going to be dividing them by binomials that look like this. This A, I hope, very clearly, obviously, is not the A we were talking about in Unit 1. So when we're talking about binomials of this form, this is a binomial of that form. And the value of A in this binomial is 7. If we're talking about x plus 5, that is a binomial of that form, and x is equal to negative 5. Are you with me on that pattern? That algebraic substitution of A into x minus A. Okay, I want to point out to you that very often, rather than saying A is 7, I will say the 0 of the binomial is 7. And the 0 of the binomial, the 0 of this binomial, is the value of x that makes it 0. So if I have x minus 7 and I say, what value would you put in for x to get 0 for x minus 7? The answer is 7, yes? So A is 7. A is always the 0 of the binomial. What value, we can even do this. What's the solution to that little equation? Well, you would subtract 5 from both sides. You would get x equals negative 5, which tells you negative 5 makes the factor 0, which means we call A the 0 of the binomial. Not necessarily very important for today, but if you get used to that language, it will be helpful for Monday's lesson. It turns out, and we have to go way back, maybe even for some of you to elementary school, that when you perform division, there are 4 players involved. There's a dividend, there's a divisor, there's a quotient, and there is always a remainder. Now, the remainder might be 0. And if the remainder is 0, that means whatever you divided by is a factor of what you started off with, and that becomes important for Monday. But there's a relationship between these 4 players that needs to be understood. And it turns out that when you divide a polynomial by these factors of the form x minus a, when you get the remainder, there's a relationship between the remainder and what you get when you put a into the polynomial you divided by. And I'm not asking you to fully understand what I just said, because that's what we're going to be learning. There's a relationship between p of a, which means the polynomial evaluated at a, and the remainder when you do the division. So let's get started. Without using a calculator, divide 26 by 3, state the dividend, divisor, quotient, and remainder. And this is an example that I think is useful to really understand, because later on, when you forget the relationship between these things, when you divide polynomials by binomials, you might want to go, well, let me go back to something simple, like 26 divided by 3. When you divide 26 by 3, and we're going to transport ourselves back in time to an elementary school setting, what this means is how many times can you pull 3 out of 26? Or if you had 26 Smarties, how many groups of 3 could you form? And the answer is 8. Right? And we know that because we hopefully know our multiplication table. We know that 3 times 8 is 24, but 3 times 9 is 27, and we don't have 27. So the answer in elementary school, you would write 8, but then there's a remainder. There's a leftover after you pull those groups of 3 out. So I'm not going to draw this, but if I drew 26 objects and I started circling them in groups of 3, I would get 8 circles each of 3, but I would have 2 individual things left over. And that's why the remainder is 2. This is not what we would write in Math 30-1. What we would say is 26 over 3 is equal to 8 with a remainder of 2. And, you know, we wouldn't even write that. But at least that's a little more sophisticated than a grade 4 or 5 student or whenever they learn about division, which nowadays could be grade 2. I don't know. The most important thing is, what is the relationship between all of these numbers? We have 4 numbers up here. We have 4 numbers. We have the 26, we have the 3, we have the 8, that'll do. And we have the 2, right? First of all, what are those things called? Well, 3 is called the divisor. In mathematics, when you do division, because the order of division is important, we have to distinguish between what the number 3 is and what the number 26 is. If I'm adding things together, like 26 plus 3, I don't call 26 something and 3 something else. They're added. It turns out that 26 is called the dividend, which is perhaps the least important word that we're going to be talking about today. We will not use the word dividend anymore, because if you kind of think ahead, where we're going with this, and I don't know whether you want to write this down or not, and I'm going to erase this. This is just me writing down in words what I was saying. I hope you know where you're going with this in terms of what I talked about at the beginning of the lesson, that this will be a polynomial function. We're going to be taking a polynomial function, which is the dividend, and this will be that special binomial divisor. So it isn't necessarily important that we know that the thing we start with is the dividend, because it's always going to be a polynomial divided by the divisor. Obviously, this is the remainder. And the result of division is called a quotient. But what is the relationship between those two numbers? I had written a minute ago, and I erased it, 26 divided by 3 equals, and then it was a statement with numbers and words. Well, that's not a mathematical statement. I've always disliked the word remainder, because I think it instills in students early on in math a misconception about what a remainder is. It's a leftover, that's true. But what students will say is 26 divided by 3 is equal to, is equal to 8. And then they say, with a remainder of 2, that sounds as if you want to add 2 onto this. But I hope you would agree if I wrote plus 2, 26 divided by 3 is not 8 plus 2. What is it? It's 8 plus 2/3. And you can either roll that around in your head and digest it mentally, or you can use your calculator to convince yourself that when you go 26 divided by 3, you get 8.666666. So this is the answer to the question. B. This is the answer to the question B. Actually, it's the answer to the question C. It's all the same thing, okay? So what is the answer to this? Show how 26 over 3 can be found using the divisor, quotient, and remainder. Well, you take the quotient, which is 8, and you add the remainder, which is 2, over the divisor. And again, as I'm writing that out, I wrote the 3 in the wrong place. And then what I literally did is I went back to, wait a minute, what is 26 divided by 3? And I did that in my head. I separated it out into groups of 3. Does that make sense for C? I think maybe this will make more sense. How can you find 26? Let me write down what everything is. The remainder was 2. The divisor was 3. And the quotient was 8, correct? How can you find 26 from those 3 players? Well, you multiply the 3 and the 8, and then you add the 2. So I can write 26 equals 8 times 3, 3 times 8, I don't really care, and then add the 2. Of course, this means, because of your order of operations, 8 times 3 first and then add 2. Does that make sense? I want you to notice that if you, I think this makes more sense to students. This is more obvious than this. But if you take this expression or equation and you divide everything by 3, you get the relationship written the other way. You get 26 over 3 equals 8 plus 2 over 3. Capiche? So this is something we call in mathematics the division algorithm. The division algorithm tells us the relationship between the dividend, divisor, remainder, and quotient. An algorithm is a rule. That's what the word algorithm means. I think on your handout you may have brackets there instead of the multiplication sign. It doesn't really matter. So the dividend will always be equal to the quotient times the divisor plus the remainder, or the dividend over the divisor is the quotient plus the remainder over the divisor. And once again, if you need to know these rules and you have not accidentally memorized them or you don't understand them, go back to something simple. You can even go back to something as simple as 13 divided by 2, which will give you a 6 with a remainder of 1. And then you can sort out what the relationship between all of those numbers is. Are we okay with that? All right. So I've started today at the beginning of the lesson by telling you that we're going to be dividing polynomials by binomials of the form x minus a. The process we use is called synthetic division. I used to teach long division with polynomials because we need to know that for calculus. How many of you are in calculus next semester? Okay, so I am going to be teaching you long division in calculus. I would normally teach it in this course, but you know, there's not as much time anymore with the new timetable and schedule. So it's something that we don't need to know in this course. There is a way to do what's called long division. We're going to use synthetic division, which is just a series of steps that does the division for us. Based on the fact that you know the relationship between dividend, divisor, remainder, and quotient, we're going to use that along with synthetic division. And in this warm-up, I'm going to convince you that the synthetic division, although it looks like just a bunch of made-up stuff, does actually give us the proper quotient, proper remainder. Okay? What we want to do is divide this polynomial by x minus, I believe yours says x minus 2. No? It says x minus 1. Okay. Is the polynomial match yours? Yeah, I just want to make sure, because again, I'm changing my notes this semester. Use the division algorithm to prove the process of synthetic division correctly performs the division. So we have to learn how to do synthetic division. It says divide this using synthetic division. Well, what we're going to do is represent the polynomial that we're dividing by, as 2, negative 4, 3, negative 6. We're simply going to write down the coefficients of every term from the highest degree term down to the degree 0 term. So there's a degree 3, a degree 2, a degree 1, and a degree 0 term. We're going to put a box here. The box looks like that. The box needs to be constructed so that you're going to have room below the numbers you've written to put more numbers. I've told you we don't use the textbook. I don't assign anything out of the textbook, but I've given you access to the digital textbook in case you feel you need extra practice with stuff. I will tell you right now that the method of synthetic division used in your textbook is different than this. I think this is better. And I'm not claiming I'm better. This textbook is the only textbook I've ever seen in high school math that does synthetic division the way it's doing it. Okay? I think this is easier, and I think all other textbooks would agree. What you're going to now put to the left of this box is the zero of the binomial. In other words, you're putting a. I hope it's not lost on you that x minus 1 compared to x minus a tells us a is 1. Right? So you put a outside of the box, and then inside of the box you put all of the coefficients of every term from the highest degree term down to degree 0 in the right order, and you bring down the first coefficient. And that's the setup. That's the setup. Now what you do is whenever you have a lone number below, or a number below that you've just brought below, you multiply by a. So we're going to take 1 times 2. That's simple. And we're going to write that 2 in the next available opening above the line. And then we're going to add the numbers in that column and write the total below the line. And we're just going to keep going. Okay? So negative 4 plus 2 is negative 2. It's not even a puzzle. It's just a pattern that we're following. And now we have a number below the line. We're going to multiply the 1 by the negative 2. Now, if I showed you long division, you might start to understand why this works, but I'm not doing it this semester, so just trust me, it's going to work. So 1 times negative 2, and we write that number up here. And then we add. 3 and negative 2 gives you 1, and we put that number below. We multiply the 1 that's a by this 1 below, and we get 1, and we add, and we get negative 5. And I always, when I do synthetic division, my brain turns on to autopilot or cruise control with these things. And sometimes I find myself writing stuff down and saying stuff without even thinking about it, what I'm doing. So I always double check. Double check everything. 2, negative 4, 3, negative 6. The value of a is 1. I bring the 2 down. 2 times 1 is 2. Plus the negative 4 is negative 2. Negative 2 times 1 is negative 2. Plus the 3 is 1. 1 times 1 is 1. Plus the negative 6 is negative 5. Good? So far, so what? What is this telling us? Well, it turns out that this is the quotient well, it represents the quotient. And this doesn't represent the remainder. This, in fact, is the remainder. But what do I mean by the quotient? What do I mean when I say 2, negative 2, 1 represents the quotient? Just in the most general sense, when you take a look at a cubic polynomial, something that has x to the 3, if I divide x to the 3 by x to the 1, I should get x squared. A cubic divided by a linear should remove one of the degrees of x from the cubic and be left with quadratic. Well, that's what this is. The quotient are the coefficients of the quadratic result of the division. So, according to synthetic division, when I take this polynomial and I divide by this, well, I'll just say divisor, I get a quotient of 2x squared minus 2x plus 1 with a remainder of negative 5. Now, for all you know, I could have just made that up, right? But luckily for you, we have a way to check. Just like This example, if I take the quotient times the divisor and add the remainder, it gives me 26. If in this example, I take the quotient times the divisor and add the remainder, I have to get the polynomial I started off with. And this is my way to convince you that what we're doing is not just gibberish. It has a meaning. So what we need to do, and I prefer to use this one, is say the quotient multiplied by the divisor plus the remainder has to give us the original polynomial. I don't, if I have a choice, I don't like using polynomial over divisor equals quotient plus remainder over divisor. Well, let's do that. The quotient is 2x squared minus 2x plus 1. We need to multiply that by the divisor of x minus 1, and then we need to add the negative 5. And this is supposed to give us the original polynomial. So how do we go about multiplying that quadratic by that linear? We use the distributive property, which says we're going to multiply every term in each factor by every term in the other factor. Everybody in the first group dances once with everybody in the second group. Okay, so I don't like drawing a whole bunch of arrows here. I think it makes it convoluted. I would just start with the 2x squared and go 2x squared times x. So far, so good, because we want a 2x cubed. I would then go 2x squared times negative 1. I would just stop and double check. What I have done is I've multiplied the 2x squared by the x minus 1. So 2x squared times x is 2x cubed. 2x squared times negative 1 is negative 2x squared. And what I do if I'm doing this on paper is I just put a little check mark above that, telling me that I'm done with that part of the product. Now I move on to negative 2x, and I say negative 2x times x is negative 2x squared, and there's no reason why I wouldn't write it here. Because I'm going to be simplifying by adding similar terms. So x squareds and x squareds are things that can be added together. And negative 2x times negative 1 is positive 2x. Doesn't matter where I write it, I can write it here. And again, I would double check that. The negative 2x times the x is negative 2x squared. I'm pretty sure I said squared, but I wrote cubed. Negative 2x times x is negative 2x squared. Negative 2x times negative 1 is 2x. Are we good there so far? Okay. And I would put a check mark there if you need to be more organized. Now I move on to the 1, and I say 1 times x is x. 1 times negative 1 is negative 1. Don't forget about this negative 5 over here. Right? That's important. What is it I get when I add this all together? 2x cubed minus 4x squared plus 3x minus 1 minus 5. And if we take a look back up at the top, we have 2x cubed minus 4x squared plus 3x minus 6, which is what we have there. Okay? It works. And again, if we had more time, I would be teaching you long division to convince you that synthetic division gives the same result. But I decided that I would just use the division algorithm to prove that this is the case. This does in fact equal to p of x. And I think it's important. I mean, I know you know I would never just make something up and teach you it. So I'm teaching you synthetic division because it works, but I always think it's important for students to understand that it does work, to see that it works, rather than just go, okay, I'll accept it on faith. So now we get to an example which is going to demonstrate a very important relationship in this lesson. This lesson is called the remainder theorem. This example is going to teach you the remainder theorem. And what I told you is that there is a relationship between the remainder of the division and the value of the polynomial when you put x equals a in. So if we go back to this, our value of a is 1. I'm telling you there's a relationship between what you get when you put 1 in for x here. There's a relationship between that result and the remainder of the division. negative 4x squared, 7x, and negative 2. So you will pick up on this pattern. If you have a degree 4 polynomial, you will have 5 numbers in here, because you have to have a number for degree 4, 3, 2, 1, and 0. Take a second and double check to make sure you write everything down correctly, which is what I'm doing right now, and it looks okay. Bring down your leading coefficient. Multiply and add, multiply and add, multiply, until you can no longer, until you've hit the end of the road. So 2 times 2 is 4. I add the 4 and the 0 above it and get 4. 2 times the 4, and when I say 2 times the 4, I'm talking about multiplying this 2 by the 4, is 8, and I put 8 here, and I add these and get a 4 again. 2 times 4 is still 8. I add these and get 15. 2 times 15 is 30, and I add these and get 28. Double check. I always double check synthetic division. They're just numbers. There's no real algebra here, but you want to make sure. 2 times 2 is 4, add, you get 4. 2 times 4 is 8, add, you get 4. 2 times that 4 is 8, add, you get 15. 2 times 15 is 30, added to negative 2 is negative 28. We're okay with that. All question A asked is, what's the remainder? The remainder when you do this division is 28. Okay, so what? Well, let's move on. Let's check out something else. Our divisor was x minus 2. I've already explained this enough that I feel as though I shouldn't even need to put a question here. But the value of a is 2, correct? What is the value of f of a? So f of x is this, correct? So what does it mean to say what is f of a? It means what is f of 2? What does that mean? It means we're going to put 2 in for x everywhere. And I don't need a set, I don't need a set of brackets here, but I think it is maybe a little bit better. Particularly if you did have a negative value of a, you would be using brackets. 2 times 2 to the 4 minus 4 times 2 squared plus 7 times 2 minus 2. Now, I'm going to teach you a way to kind of cheat a bit, particularly on written response. Legitimately cheat. Do you agree that calculating this, particularly if a was negative, would be fraught with potential for errors? Okay, it's a lot of exponents and multiplication. So what we can do, and I hope that, I know my Math 20 students from last year have been exposed to this, but I don't know about anybody else. What we can do is use the table features of our calculator. So I'm going to go in here, and I'm going to put for y1, 2x to the 4 minus 4x squared plus 7x minus 2. And this is the way I enter things, because visually I can see if I have the right number of x's. Okay. You can certainly put 2x to the 4 minus 4x squared plus 7x minus 2. So I'm putting the polynomial that y is equal to on this graph, although I don't want to look at the graph, in for y1. I'm going to go to my table setup and ensure that it says ask. I want to just do something first. Don't worry about it. I want to go to my table setup and ensure this says ask. What I just did was made sure there's going to be nothing in my table, because I had some things in there. So that second window, and I highlight and enter at ask, and I go here, and it's not going to say, hey, Paul, what do you want for x? It's just waiting for an answer, though, to a question that's unsaid. I'm going to put in 2. And then it calculates the value of p of 2, and as long as I double check that I've entered p of x incorrectly, I get that answer. Noah, you get that? So you're going, because you're recognizing the number 28, I think. It's the remainder. So what do you get? You get f of 2 equals 28. Do you notice about the relationship between the remainder when you divide by x minus 2 and f of 2. You learn that f of 2 equals the remainder when dividing by x minus 2. This is the remainder theorem. There's a connection between f of a and the remainder when you divide by x minus a. Now, I've got here a question that I decided to add last night. Does it work with other binomials? Well, let's just try something. Let's do the polynomial function divided by x plus 7, which means a is negative 7. So first of all, imagine putting negative 7 in for x in the polynomial and trying to manually calculate it. It's complicated. The synthetic division, I think I need some help here. 2, 0, negative 4, 7, negative 2. Wow. Surprised myself. Negative 7 goes here. So just one final double check. These numbers are correct. I might regret choosing a number like negative 7 for a, but we'll just do it. 2, multiply, you get negative 14. Add, you get negative 14. Multiply, you get 98. You have calculators, just is negative 7 times negative 14, 98. Okay? 98 plus 4 plus negative 4 is 94. 658, negative 658. Okay. Here's where I'm going to run out of steam. Negative 651. $47.59? No, rats. 650, so 4,200 plus 350 is 45.50. 45.57. I'll just, yeah? Second time, okay. 45.57. So just double check those last series of numbers that I've written. Good. I add these and I get 45.55. So does it work with other numbers? Well, we're not going to stand here and choose every number in the universe. We would never get anything done. I've demonstrated that it works with at least one other number, and I wouldn't be doing this if it didn't work with all numbers. So the answer is yes. Now, if I asked you to find the remainder when you do that division, wouldn't you rather do this than synthetic division? All right, we're going to run through some examples here. The remainder theorem says when you divide a polynomial by x minus a, the remainder is p of a. I'm using p of x and p of a here. So if I said to you, what is the remainder here? What I do not want you doing is synthetic division. If that's the only goal, what we need to do is find p of 3. Because a is 3. That means we need to take 2 times 3 to the 4 plus 3 times 3 cubed plus 4 times 3 minus 1. Now, you know, in this particular case, I wouldn't use my tables because I can calculate some of these numbers fairly easy. I know, for example, that 3 to the 4 is 81. It's 9 times 9. I know that this is 3 to the 4, so it's another 81. I know that I'm adding 12 and I'm subtracting 1. I don't care how you cut it. You need to be able to calculate what this is equal to, and it's equal to 254. Okay? So the remainder is 254. Could you have done this question with synthetic division? Without a doubt, as long as you put 0 in for 0x squared. Can you do this with synthetic division? Yes, but I would say you open yourself up to the potential of more mistakes. You're more likely to make a mistake with synthetic division here. We need to find, for the remainder, p of negative 2. Now, I just finished saying I can do this without the table feature of my calculator. Honestly, I'm not so confident here. So if this were a written response question, and you were asked to find the remainder, you would say, I'm going to calculate this and then you're going to write the answer. You're going to put the polynomial in your y, go to your table, and enter negative 2. Do you get my idea here, that you're kind of cheating behind the scenes? You don't have to explain to the marker on a diploma exam how you got this. You just need to be able to get it. And I don't know, some of you might be quicker at just entering that in. I mean, negative 2 to the 5 is negative 32. You could do it that way. But I'm going to go 3x to the 5. Is it plus another 3? It is. Plus 3x cubed plus 4x squared plus 5x minus 1. When you do this, you want to just triple check to make sure that you've entered it correctly before you go to your table, because you're about to leave it behind. You go to your table, you won't see it anymore, right? So when you go here, you're acting on faith that when you enter negative 2 and get negative 115, it's correct. So the remainder is negative 115. I hope you see why, if you want to do this third one with synthetic division, I would say have at it. But I hope you see that you would not want to. Because you're going to have to write 3, and then a whole bunch of zeros down to the 7, and then a 0 and a 5 and a negative 1. So what is the remainder? The remainder will be p of negative 1. I'm not going to do this with my tables. A negative raised to an odd exponent retains the negativeness of it. I don't need to figure out what negative 1 times itself 109 times is. It's going to be negative 1. I would not give you this question with x plus 2, because then your number would be explosively large. So this is going to be negative 3. This will be negative 7. This will be negative 5. And this is negative 1. And we can add them together and get what I believe to be negative 16. Are we okay with that? All right. We have a polynomial. We do not have a polynomial function, but when we've been dividing the polynomial functions by x minus a, we've just been dividing what the function is equal to. We haven't included the y. So if this bothers you that it doesn't say y equals or f of x equals, I guess it would be f of r, wouldn't it? Does this match your example? Okay. It doesn't matter. It tells you that when you divide this polynomial by r minus 3, you get a remainder of 12. What does that mean? It means that, and if you like, you can call this p of r. I'm just going to say p of 3 equals 12. The remainder theorem says, whatever that remainder is, when you divide by x minus a, or r minus a in this case, you get that remainder. A is 3. So this is a way of me saying to you, when I put 3 up here for r, I have to get 12. Hang on 1 second, please. What we have in this question is a missing parameter. Now way of looking at things here is not that it's a missing parameter for a graph of a function, so we need to put in the coordinates of a point. But we need to put in something for r in this expression and set it equal to what it's equal to. So it's like putting in a point. If you want you can just imagine it that way, and we have a missing parameter, so you need to put in an x and a y. Well, x is the value of a, y is the remainder. But once again, we're just saying when you put 3 in for r, you have to get the remainder. That's what the remainder theorem says. But you're told that the remainder is 12. So from a equation standpoint, you now have an equation with one unknown, which is k. We can simplify this. 3 cubed is 27. 3 squared is 9, so let's just write 9k. 17 times 3 is 51. Pretty sure on that count. Plus 6 equals 12. Solving this now is a junior high question, right? In fact, I would say that this line right here became, grade 9 is maybe pushing it. If you gave that to grade 9s, they'd probably just panic and freak out. But grade 10 for sure, you can solve this, right? But now we've turned it into, like, for sure, a junior high question. How you solve it in junior high might be different in your head. Here, what I would do is I would add 9k to both sides and figure out what all of these numbers on the left minus 12 are equal to. I want to say 72. So you need to figure out for me to confirm that 27 plus 51 plus 6 minus 12 will give you 72. And it does. So that means that k is equal to 72 over 9, which is 8. Which is 8. So that parameter is 8. That's it. That's all. So there are 11 questions on the pages following this lesson that you're working on. You have a little less than 15 minutes.